Hi everyone, welcome to My Max Academy. In this session, we'll continue with the chapter Real Numbers from 10th standard CBSE Mathematics. I'll continue from Theorem 1.5 in page number 16 in your textbook. So page number 16, Theorem 1.5. Fine. So what it says is Theorem 1.5. Let x be a rational number whose decimal expansion terminates terminates, then x can be expressed in the form p by q, where p and q are coprime, comma, and the prime factorization of q is of the form 2 power n 5 power m, where n comma m are non-negative integers. So this is the theorem 1.5. So it says that let x be a rational number whose decimal expansion terminates, then x can be expressed in the form p by q, where p and q are coprime and the prime factorization of q is of the form 2 power n 5 power m, where n and m are non-negative integers. So now if you read this statement, it may be a little confusing. So if I give you example, it may be confusing, but for some people it may be clear. If I give you example, then you can understand this theorem. Right? So what it says is x is a rational number whose decimal expansion terminates, which means the decimal expansion or the decimal part of that number stops. Terminates means stops. Then we can write, or we can express x in the form of p by q, where p and q are coprime. P and q are coprime means you cannot simplify this further. This fraction x is equal to p by q is in the simplest form, which means you can't reduce this fraction further. You can't cancel out any common factor and reduce this further. And the prime factorization of the q is of the form 2 power n 5 power n. 2 power n 5 power m, where m and n are non-negative integers. So what it means is, whenever you can write x as a form of p by q in the simplest form of the fraction, after cancelling out all the common factors, you are writing that x as p by q, where p and q are coprime, means there is no number that will divide p and q. P and q are coprimes means there is no common factors between p and q, which means if you write x as a simplest form of the fraction, after cancelling out all the factors, if you write as p by q, and then if you check the denominator q, it will be of the form 2 power n 5 power m, where n and m are non-negative integers. So I will give some examples to explain this. So let's take an example. Suppose if x is equal to some example. So examples are, suppose I am giving one example. Let's take 0.375. This is my x. X is equal to 0.375. Now what is the decimal expansion of this? Decimal expansion is, after the numbers that we have, the 375, and it stops. It terminates. It doesn't go. So 0.375 and then it stops. After that we don't have any other number. It stops. So which means the decimal expansion terminates. That's why we call that as a decimal expansion terminates. Then we can write x in the form of p by q. Right? How do we write x as? How do we convert this decimal into a fraction? So I will write x as 0.375 by 1. Right? So any number has always denominator 1. Right? So we are going to convert the decimal into the fraction form, because it says that whenever it has a terminating decimal expansion terminates, then x can be written in this form. So I should write x in this form. So which means I need to convert x as a fraction, p by q. So which means to convert this, we will multiply by 1000, divide by 1000, because we have 3 numbers after the decimal. So if you need to convert the decimal to fraction, we will have to multiply with those many zeros, 3 zeros, because we have 3 numbers. So we have to multiply by 1000. If it is two digits after the decimal, you have to multiply and divide by 100. Now 0.375 into 1000 will give you 375. By 1 into 1000 is 1000. Now x is equal to 375 by 1000. Now we have expressed in the fraction form, in this form, p by q, but we have to make sure that we reduce this to the simplest form so that p and q are co-prime, which means we need to simplify this. So this is not equal to this form, that p and q are co-prime. It is in this form, but p and q are not co-prime. This is p, this is q. Suppose if we take this as p, this as q, they are not co-prime. Co-prime means we have some common factors. You have to simplify this. The simplest, after simplifying this fraction, whatever fraction you get, that should be taken as p by q. So if I simplify this, I can cancel this with suppose 5, right? If I cancel with 5, what do I get? 5 7s are 35, 75 by, if I divide by 5, I'll get 200. Now again I can divide this by 5. If I divide this by 5, I'll get 75. If I divide by 5, I get 15. By 200 by 5 is 40. Right? And again I can simplify this. I will get again by 5, 3 by 8. Now can I further simplify 3 and 8? No. Because there is nothing that will divide both 3 and 5. I can't cancel 3 and 8 with any common number. Right? So which means now x becomes 3 by 8. This is in the form p by q. Now this is, if we write x as 375 by 1000. Now here it is not in the form of p by q. After simplifying the simplest form of the fraction, the simplified fraction, that you should call it as p by q. Now it is p by q, 3 by 8. So we have expressed x in the form of p by q, where p and q are co-prime. Here p is 3, q is 8. This is not p and q. 375 is not p, 1000 is not q. After simplifying the fraction, the simplest form is called as p by q. Right? Now this is p by q. Now we have to take the denominator, where p and q are co-prime, which is true. 3 and 8 are co-prime, which means there is no number that divides both. Or the HCF, the highest common factor between 3 and 8 is what? 1. 1 is the only number that will divide 3 as well as 8. No other number will divide, because it is in the simplest form. The fraction is in the simplest form. Right? Now we should check the prime factorization of q. Q is what? The denominator. What is q here? Q is 8. Then q will be in the form of 2 power n 5 power m, which means 2 is in the form of, so which means I can write my q as, how will you write 8? 8, we will do the prime factorization. So 2, 4, 2, 2, 2, 1, which means 2 into 2 into 2, 2 cube. 2 cube, which means it is in this form. There is no 5 here, but you can always put 2 power 3 into 5 power 0. We can put this as 2 power 3 into 5 power 0. I can write it down. Say 8 can be written as 2 cube. So q, I can write this in this form. 2 power 3 into 5 power 0 I can put, because 5 power 0 is what? This is into 2 power 3 into 5 power 0 is what? 1. Right? Now it is in this form. Your n and m are non-negative integers. Non-negative means they can be positive or 0. The powers of 2 and powers of 5, can be positive or 0, but it cannot be negative. See, power of 2 is what? 3. Power of 5 is 0. where 3 and 0 are non-negative integers. Non-negative means they are not negative. 3 is not negative and 0 is also not negative. Right? So now q is in the form of 2 power 3 into 5 power 0. If there is nothing is there, then we can put it as 5 power 0. So whenever x has a terminating decimal expansion, you can write the denominator in the form of 2 power m 5 power n. Clear? Now we will take one more example. Probably suppose suppose x is equal to, next example, suppose x is equal to, I'm just explaining this theorem, x is equal to 0.4. X is equal to 0.4. Now how do we convert this in the form of p by q, and then we have to simplify, which means we need to convert this decimal into a fraction. So which means my x will become 0.4 by 1. So into 10 by 10, because after decimal we have only one number, so into 10 by 10, this gives me 4 by 10. So my x is 4 by 10. But this, we cannot say this x is equal to 4 by 10 is p by q. No, you have to simplify this. Simplify this. So 2 2s are 4, 2 5s are 10. Now my x becomes 2 by 5. Now it is in the simplify. I cannot further simplify this. At this stage, now this is my p and q. This is my p, this is my q. Now what is my q? Then I have to check the denominator q. Q is what? 5. Q is 5. So if I do the prime factorization for 5, 5 ones are 5 only will come. 5 ones are 5 only will come. So which means q is 5. Then which means I can write q as 2 power 0 into 5 power 1. 5 means 5 power 1. Now we have expressed q in the form of 2 power n, 5 power m. So the power of 2 can be 0, power of 5 can also be 0. The only thing is it should be positive, the power should be positive or 0. It cannot be negative. It cannot be negative. So whenever q has only these two, it should not have 3 power something or 7 power something. It should not have any other number other than 2 and 5. It can have 2, it can have only 2, it can have only 5, or it can have 2 and 5. Right? So this is one example. Right? So whenever the other 2 is here, only 5 is there, 2 is not there, then you can always put 2 power 0. Whenever it is not there, you can always put 2 power 0. Here also you can put, here it is 5 power 1. 5 means 5 power 1. The 2 is not there. Whenever 2 is not there, you can put 2 power 0. Here 5 was not there. So we put 5 power 0 so that we get it in this form. Right? Now we will take one more example. Suppose if I take third example, suppose if my x is 0.025. Then I can write my x as 0.025 by 1. I should say into 1000 by 1000. My x will become, to multiply this with 0.25 into 1000 will give me 25 by 1 into 1000 is 1000. Now if I simplify this, we cannot stop here. Don't think I have gotten the form of p by q. Now you have to simplify. The simplest form which cannot be further reduced, that is called as p by q. There only you have to check what is q. Here itself you can't take your q as 10. Or here you cannot take your q as 1000. You have to simplify, and the simplest form, after simplifying the fraction, then you have to take the denominator, and that should be called as q, and then check whether that q is in the form of this, and that q will be in this form. Whenever x has a decimal expansion terminates, your q will be in this form. That's what the theorem says. Whenever x is a rational number and the decimal expansion terminates, then x I can write it as p by q, where p and q are co-prime, and the denominator q, after simplifying, after making p and q as co-prime, after that, if I try to find what is the denominator, then that denominator will be in the form of 2 power n, 5 power m, where m and n are non-negative integers. No? So now if I simplify this, 5 5s are 25, then this is 200. So 5 by 200. If I again simplify this, I'll get 1 by 40. So my x is 1 by 40. No, I can't simplify this further. I cannot simplify this further. Now this is the simplest form. Now at this time, x is expressed in the form of p by q, where p and q are co-prime, which means 1 and 40 are co-prime. No number will divide both 1 and 40 except 1. Except 1. No other number. Right? We call two numbers as co-prime if their HCF is 1. The highest common factor between the two numbers is 1 means, then we call those two numbers as co-prime, which means there is no other number that can divide both. There's no number which is common to both the numbers except 1. Right, now we have got it in this form 1 by 40. Now what is my q? Q is the denominator, which is 40. Now 40 can be written as what? We'll do the prime factorization for that. So 40, I will write 2 times 20, 2 times 10, 2 times 5, 5 times 1. So 2 into 2 into 2, 3 2s and 1 5. So 2 cube into 5. So q is 2 cube into 5 into. Here also into. Here also into, right? So 2 cube into 5. Now is this q in the form of 2 power n, 5 power m? Here your n is 3 and your m is 1. 5 means 5 power 1. So whenever your x is having a decimal expansion and that terminates, then we can express x in the form of p by q, and then where p and q are co-prime, we have to simplify and write the x equal to fraction form, the simplest form of the fraction, right? That is p by q. That time we should go and check the denominator, and you will see that the prime factorization of the q, which means when you do this, it will have only it will be in the form of 2 power n, 5 power m, which means it can have either 2, it will have only 2 or only 5 or both 2 and 5, like this, only 2 or only 5 or 2 and 5 both. It should not have any other number like 3 power 3 or 7 power 2. Nothing should come like that. It will not be like that. So this is what is theorem 1.5. Fine. Now I will explain theorem 1.6. So let's go to theorem 1.6. So next one is theorem 1.6, which is in the same page 16. Right. So what it says. Let me erase this. The theorem 1.6 states that let x is equal to p by q, and again be a rational number. Be a rational number, and they should have given here that where p and q are co-prime. P and q are co-prime, right? Such that the prime factorization of q is of the form 2 power n, 5 power m, which means 2 power n into 5 power m. That is the meaning of this. Where n comma m are non-negative integers, then x has a decimal expansion which terminates. So what it says is, suppose if x is in the form of p by q, after cancelling out all the common factors where p and q are co-prime, and suppose if you check the denominator, if the denominator is in the form of 2 power n, 5 power m, the denominator is q. If q is of the form 2 power n, 5 power n, then where n and m are non-negative integers, then I can say x will have a terminating decimal expansion, which means the decimal expansion of x will terminate, which means when we convert this fraction into decimal, and that decimal will stop, it will not continue, it will not keep on going, it will not be non-terminate, it will terminate, which means it will stop. It's basically the reverse, the converse of the earlier theorem. 1.6 is the converse of 1.5. See, 1.5 says if x's decimal expansion terminates, then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q will be in the form of 2 power n, 5 power m. So it says, the earlier theorem 1.5 says if it has a terminating decimal expansion, then the x can be in the form of p by q, then where p and q are co-prime. At that time, when you find the q, and then if you do the prime factorization for q, that will be in this form. But this theorem says if q is in this form, when you write x as a fraction, and then if you simplify, cut out all the common factors and write it as a simplified fraction, which means p and q are co-prime, and if the denominator is in the form of 2 power n 5 power m, denominator is q, if the q is in the form of 2 power n 5 power m, where n and m are non-negative integer, then we can say that x will have a terminating decimal expansion. It's just a converse of the earlier theorem. So I will do some examples, then I will use the same example to explain this. Fine. So let's go, let me erase this. Here x cannot be decimal. You have to, so x is 3 by 8. Suppose x is 3 by 8. X is 3 by 8. Now what we should do is, suppose x is 3 by 8 like this, and then it is in the simplified form. Whenever x is given in the form, you check whether it is simplified. If not, you should simplify and make it in the simplified form. Or we can take another example. I will give it as 6 by 16. Suppose x is 6 by 16. Let's take this example. Now we cannot say x is in the form of p by q, because first you have to simplify this. Can I simplify this? Yes, I can write this as 2 3s are 6, 2 8s are 16. 2 3s are 6, 2 8s are 16. So I can simplify and write it as 3 by 8. So given number is what? 6 by 16. So my x becomes 3 by 8. Can I simplify further? No. Now at this stage, this is called as p by q. Right? And what is my q's? Q can be written as what? Q is 8. So Q can be written as 2 cube. Like this, 2 into 2 into 2. So Q becomes 2 cube. So which means Q can be written as 2 cube into 5. 5 power 0. 2 cube into 5 power 2 cube means 2 cube into 5 power 0, because value of 5 power 0 is 1. Now Q is in this form of 2 power n 5 power n. Right? So we'll say Q is of the form 2 power n into 5 power m. So the moment the Q is in this form, then this 6 by 16 will have a terminating decimal expansion. So Q is of the form 2 power n 5 power n, where n comma m are non-negative integers, which means the powers of 2 and powers of 5 cannot be negative. Powers of 2 is 3, power of 2 is 3, power of 5 is 0. It can be 0 or positive, but the powers cannot be negative. So therefore we can say x equal to 6 by 16. X is equal to 6 by 16 has a terminating decimal expansion. Which means if you convert 6 by 16 into decimal, right? If you do the normal division, see, we have say 6 by 16. If I simplify, I get 3 by 8. Then if I divide my 3 with 8, so 0.30, 30 goes point, and then 30 goes 1, 2, 3, 3 times, 24, then 6, that goes 7 times, 56, then 4, 40, 40 goes 5 times, 40. So you will get the remainder as 0, which means the decimal will stop here. 0.375 ends here because we get the 0, stops. So without even dividing like this, we can say it will stop. Without even dividing, we can say that it will stop. It will have a terminating decimal expansion, which means the decimal part will stop, or the decimal expansion will stop without even doing this. You can say why? Because my Q is in the form of 2 power m 5 power 2 power n 5 power m. So whenever they give you a fraction, they will ask you check whether it has a terminating decimal expansion or non-terminating but repeating. That is coming in the next theorem. Then you have to take that given fraction, simplify this, in the simplest form, then try to, after getting that into the simplest form, then go and check the denominator, which is q, then do the prime factorization for that. You will get 2 cube, then which means 8 can be written as 2 cube, then q is 2 power 3 into 5 power 0, then q is in the form of this. Therefore we can say x will have a terminating decimal expansion. Whenever the q is in this form, you can say it has a terminating decimal expansion, right? We'll take one more example. Suppose we need not divide, so without dividing we are going to say, here I divided and show you that yes, it is stopping, right? So now the next example is x is equal to, suppose if I take 4 by 10, then we have to first simplify, right? We cannot take as p by q. First if I simplify this, I get 2 by 5. 2 2s are 4, 2 5s are 10, so 2 by 5. Now what is, can I simplify further? No. The moment I simplify to the lowest form of the fraction, at that time I should go and take my q. Now what is my q? Q is 5. Now that q can be written as 2 power 0 into 5 power 1. Where 5 means 5 power 1, 2 power 0 is 2 power 0 value itself is 1. So 5 can be written as 2 power 0 into 5 power 1. So now what? Q is in the form of Q is of the form 2 power n 5 power m, where n comma m are non-negative integers. Therefore we can say, using this theorem 1.5, therefore x will have, x is what? X is equal to 4 by 10 will have terminating decimal expansion. We can say that. We need not even divide. If you divide and find, you will get 0.4. 4 by 10 is what? 0.4, which means it stops. The decimal stops. That's the meaning of terminates. Terminating decimal expansion means the decimal part of the number will stop. It will not keep on going. Right? We have fractions where it will keep on going. If I take 1 by 3, if you try to find the decimal equivalent of 1 by 3, it will become 0.333333. It will keep on going. So which means the decimal expansion does not terminate there. So it's non-terminating. Non-terminating means it is not stopping. Non-terminating, but there it is repeating. If you take x as 1 by 3, that will not get into this. Right? So this will have a terminating decimal expansion. Now next one, we'll take one more example. Suppose if x is, we need not find the decimal value of that they have not asked. What is the decimal equivalent of 4 by 10? 4 by 10 you can immediately say it is 0.4. But here the point is, whenever x is in the form of p by q, where p and q are co-prime, and the denominator q is in the form of 2 power n 5 power m, 2 power n 5 power m, then we can say that the x will have a terminating decimal expansion, or the decimal expansion of x will terminate, which means stop. The decimal part will stop. Here it stopped. Here also 4 by 10 means 0.4. It will stop. So you need not divide actually. Without dividing, you can say it will whether stop, or the decimal part will end, or it will terminate, or it will be non-terminating and recurring. Just looking at the denominator. The denominator should be in the form of 2 power m into 5 power 2 power n into 5 power m. Then you can say it has a terminating decimal expansion. Right? See, that's what. Here it had only 2. Here it has only 5. Then also it is in the form of 2 power n 5 power m, because you can always put 5 power 0. Here you have only 2 cube, but still I can write it as 2 cube into 5 power 0, because 5 power 0 is 1. So 2 cube can be written as 2 cube into 5 power 1, 5 power 0. 2 cube can be written as 2 cube into 5 power 0, because the value of 5 power 0 is 1. So it took, why I am putting into 5 power 0 to get it in this form, because in the power I can have 0, or I can have positive numbers. I should not have negative numbers in the power. So same with the case. Here we have only 5. 5 means 5 power 1. but I need to get it in the form of 2 power n, 5 power n. Then I can always put 2 power 0. Then I can always put 2 power 0 to get it in this form. Fine. Now we'll take one more. Suppose if x is equal to another fraction 14 by 560. Suppose 14 by 560. Then if we simplify this x, if we cancel by 7, 7 2s are 14, then this will become 7 8s are 80. So we'll get 2 by 8, 80. Then we cannot take this as again p by q. Because you have to check whether can I simplify this further. Yes, it can be simplified further. So x will become, if I cancel 2 1s are 2, 240. So 80. So it becomes 1 by 40. So now this we have simplified. I can't simplify this further. 1 by 40 is the simplest form of the fraction. At that time, we have to go and check. After making the x in the form of p by q, where I cannot further reduce, that time we call that as a p by q. At that time, you have to go and check take the denominator q. Denominator is 40. Numerator is p. P is 1, q is 40. Now you have to check, go and check the denominator only. Then q equal to 40. Now for 40, let's try to do the prime factorization. So 2, 20, 2, 10, 2, 5, 5, 1. So which means it can be written as 2 into 2 into 2 into 5. Which means 2 cube into 5. So which means my q can be written as 2 cube into 5. Into 5 means 5 power 1. So what we see now, q is of the form 2 power n, 5 power m. So therefore q is of the form 2 power n, 5 power m, where n comma m are non-negative integers. Non-negative integers. So therefore, by this theorem 1.6, we can say x is equal to 14 by 560 will have terminating decimal expansion. Therefore, we can say it will have a terminating decimal expansion. Clear? So that is what the 1.6 says. Theorem 1.6 says this. Fine. So now I will I think these 3 examples are fine. I will stop here and I will continue in the next video, the next theorem, which is theorem 1.7. So please watch my next video for the continuation of this, where we will do theorem 1.7 continuation of this. Thank you for watching.